Welcome back to my lectures on Galois theory. Our next topic is the isomorphism extension theorem. We have been discussing about algebraic extensions and automorphisms. This automorphism has a big role in studying the structure of algebraic extensions. So, to properly study the structure of algebraic extension, we need to develop automorphisms from existing isomorphisms. And finally, what we are going to do is to establish a nice relationship between algebraic extensions and the group of automorphisms. And that's what Galois theory is all about. So our objective is to develop or create automorphisms from known isomorphisms. In an algebraic extension, let E be an algebraic extension of f and alpha belongs to E be algebraic over f. Of course, if alpha is in E, it's always algebraic. Then there exists a conjugate isomorphism denoted by alpha comma beta from f alpha to a subfield of E, where beta is a conjugate of alpha. We already established this one. And what are the properties of this? Alpha comma beta of alpha is equal to beta, and alpha psi of alpha beta leaves f fixed. So we know about the existence of an isomorphism. So we want to develop some mechanism to create automorphism from the known isomorphisms. So once we have the automorphism, it is easy to study the structure of the algebraic extension. So in this topic, we are trying to extend this isomorphism to a higher, an isomorphism with a larger domain. Okay, and that's what this topic is all about. Now let us define what an extension is. Extension of an isomorphism is. So let F be a subfield of E and F prime be a subfield of E prime. In this case, you say that E is an extension of F, E prime is an extension of F prime. And let phi be an isomorphism from F to F prime. So it's going to be like this. E, F, E prime, F prime. We have an isomorphism here from F to F. Then an isomorphism tau from E to a subfield of E prime is an extension of phi this is tau. If tau restricted to F is equal to phi. In other words, tau of A is equal to phi of A for all A in F. Meaning, if A is mapped to phi of A, then tau of A also mapped to phi of A. It is not making any difference. So that is the meaning of extension. So as far as phi is concerned, it is not changed under tau. Now let us assume that E is an algebraic extension of F and alpha belongs to E, meaning alpha is algebraic. So we know that there is a conjugate map from here, like F alpha to a subfield of E, and this is normally called alpha comma beta, where beta is conjugate of alpha, conjugate occur. So the question is whether we can extend this isomorphism from E to a subfield of F closure. F closure is somewhere here. It is actually the closure of F. So can we have an extension tau from this algebraic extension to a subfield of F closure? If you want to generalize this, it's going to be like if F is a field and F prime is another field, and there is an isomorphism here, and E is an extension of F, algebraic extension of F, then can we have a tau from a subfield of F prime closure? F prime closure is somewhere here. So once we have a extension like this, Then we can talk about automorphism and all later. So first we need to find out whether we can have an extensions like this. See, let us assume in this situation, we'll take a general situation always. So let us assume that alpha belongs to E. So E is, I'll write it here, E is an algebraic extension of F, and alpha belongs to E, meaning alpha is algebraic. This is an isomorphism, meaning these two fields are exactly same except for the names of the members. It works exactly like same. And alpha belongs to E, and alpha is algebraic. That implies there exists a polynomial P of x, and that is the irreducible polynomial of alpha, and let it be equal to a0 plus a1x plus dash 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 an xn that belongs to f of x, such that P of alpha is equal to 0. Now, under this map, what is going to be P of x? Is equal to sigma of a0 plus sigma of a1x plus dash 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 sigma of an x to the power of n, and that belongs to f prime of x. This is irreducible in f of x, and sigma is an isomorphism. That means this is an irreducible polynomial in f of x. So P of x is irreducible in f of x, implies, let us take this as q of x so that I don't need to write it again. Q of x is irreducible in f prime of x. That means there exists a beta, or probably we'll write it as alpha prime in F closure, such that Q of is equal alpha prime close equal to 0. Then we can think about a conjugate isomorphism. It's not actually conjugate isomorphism because they are coming from two different fields, but similar kind of stuff. A map, let's say phi from f alpha to f prime alpha prime. Such that phi of alpha is equal to alpha prime. And since the degree of both the elements are same, because the degree of alpha is n, the degree of alpha prime in f prime is also n, then we can define like this: phi of A0, or let's say C0 plus C1 C1 alpha plus dash 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 C n minus 1 alpha to the power of n minus 1 is equal to psi of 0 plus alpha, sorry, psi of 0 plus psi of C1 alpha prime plus dash 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 psi of Cn minus 1 alpha to the power of alpha prime to the power of n minus 1. Any element of f alpha is of this form because the degree of alpha is n and the degree of alpha prime is also n. So if you consider this map, this is almost like a conjugate map, but not exactly conjugate map because these elements are coming from two different fields. But this is an extension. This is a map from f alpha to f prime alpha, meaning it is somewhere here. So we reached here. This is our alpha. This is our phi. So we can extend sigma to phi. But we haven't reached yet here. And suppose we take another beta here and try to extend this phi to, let's say, f of alpha comma beta to f prime of alpha prime comma beta prime. With the same logic, we can get, this is probably, we'll say, phi alpha, this is probably phi beta. But still we are not yet here. If E is a finite extension of f, we can continuously extend sigma like this, taking elements from E but not in the next field. For example, here we took alpha from E but not in F, beta E but not in F of alpha. So if we continue like this a finite number of times, we will reach E. So we are done with that theorem. But we don't know if E is a finite extension of F. All we know is E is a algebraic extension of F. Doesn't need to be finite. If it is finite, this argument goes very well and definitely we can extend sigma to tau. Now we will state the theorem. Let E be an algebraic extension of F, and sigma is an isomorphism from F to F prime, be an isomorphism from F to a field F prime. Then sigma can be extended to an isomorphism tau from E to a subfield of F prime closure. So this is the theorem. If E is a finite extension of F, then we are done. There is nothing to prove because we already showed an isomorphism in n number of steps, that if E is a finite extension of F, we have a extension of this isomorphism. But this is, you don't know anything about the dimension of E over F as a vector space. So we need some tools to prove this theorem. The tool to prove this theorem is Zone's lemma. But before we come to Zone's lemma, I want to define a partial ordered set, or you can say poset. So the definition is like this: let S be a non-empty set. Define a relation normally denoted by this, by on S, on has having the following properties. One, for every elements in S, A is always related to A. It's called reflexivity. Two, if A is less than or equal to B, the relation is, we are saying relation as less than or equal to. It's actually, it's a relation, okay? And B is less than or equal to A implies A equal to B. This property is called antisymmetric. And the third one is A less than or equal to B, B less than or equal to C implies A less than or equal to C. It's called transitivity property. If these three properties are satisfied, the set S along with this is a poset. Example, let S is equal to, or let A is equal to A is equal to 1, 2, 3. Then S is equal to the power set of A, meaning all the subsets of this, along with inclusion is a poset. Meaning S is going to be 1, 2, 3, 1, 2, 2 3 3 1 1 2 3 then empty set. So if you draw the diagram, empty set is on the bottom, then you will have 1 comma 2 2 comma 3 3 comma 1, sorry, in between you have 1 2 3. So this is a subset of this, so it's related here. This is a subset of this related here, and this is a subset of this. Then you have 1 2 2 3 3 1. This is a subset of here, and this is also a subset of this. This is a subset of here, and this is also a subset of this, and this, and this. And you have 1 2 3. So all subset of this. So this is a diagram, Poisson diagram. What we need to know is 2 and 1 are not comparable. There is no relation between 2 and 1 or even 3. You cannot compare this element with this element and with this element. So there are elements in S that are not comparable. Another example is 1 comma 2 cannot be compared with 2 comma 3. There is no comparison because this is not included in this and this is not included in this. So that is why it is called partial order. If you take any two elements, there is a chance that those two elements cannot be compared. Now, a chain in a poset S is a subset of S such that any two elements from is a subset T of S. A subset T of S. Any two elements from T are comparable. For example, the chains in P of A include, I'm not going to write all the chains, include, or you can say this 1 1 2. This is a chain, and this 1 2 1 2 3. This is a chain because any two members are comparable. If you take these two, anything is comparable. Or you can say 1 2 1 2 3. These are all chains. Okay. Now I have a couple more definitions. Let S be a poset and A is a subset of S. Then an element U belongs to S is called an upper bound of A if A belongs to A implies A is less than or equal to A. It's called upper bound. Now, M is maximal if there exists no element A in S such that A is greater than or equal to M. Now we will state the zones lemma. Let S be a poset and if every chain, it's a subset of S, chain is a subset of S, every chain has an upper bound, then S has at least one maximal element. Now, I'm just going to explain how we are going to use zones lemma in proving the isomorphism extension theorem. So we are going to create a poset. So what is a poset? Poset contains elements and a relation. So the way we are going to define the poset, there is an F here and there is an F here and we have a F prime here and there is a sigma here. So our poset here in proving the isomorphism extension theorem, the S is going to be an ordered pair. The first ordered pair is F comma sigma. The ordered pair contains two elements. The first element is a field, second element is a isomorphism. Second element or the next element will take an alpha outside outside F. So we know that we can define an extension from F alpha to F alpha prime. We already saw that. So this is our next next map, and we can extend sigma from F alpha to F alpha prime, and that is probably sigma 1. So we have f alpha 1, let's take it as f alpha 1. F alpha 1 sigma 1. Now we go up another level, 2, here also 2 prime. So we'll have f of alpha 2 sigma 2. Goes like this. Sorry, this is going to be f alpha comma sigma 1. Then this will be f alpha 2 comma sigma 2. The first element of the ordered pair is a field. Second element is a isomorphism. And we have to define a relation between any of these two. See, so we are going to say, see, instead of writing like this, in a generically what we are going to write is h1 comma sigma 1, h2 comma sigma 2, hn comma sigma n, etc. So hi comma sigma I is less than or equal to hj comma sigma j if hi is a subfield of hj and sigma j is an extension of sigma I, leaving hi fixed. That implies sigma j of A is equal to sigma I of A for all A in hi. Then S is a partial ordered set. I just want to explain how we are going to develop a partial ordered set in order for us to apply Zone's lemma to prove the isomorphism theorem.